All right, greetings YouTube, beautiful mind here. Let's see, so we're going to continue some of our exploration with applications of derivatives. We're moving on to section, so this is still chapter 3, applications of differentiation, and we're moving into section 3.2, using second derivatives to find max and min values in sketch graphs. Some objectives here are to classify the relative extrema of a function using the second derivative test and graph a continuous function in a manner that shows concavity. So what we kind of looked at last time was the first derivative test. Given a function, we can identify local max or min. That's where the derivative, the local max or min of a graph or a function is going to be where the derivative is either going to be equal to 0 or where the derivative is going to be undefined. Those would identify critical values. So the first derivative will give us a sense of whether the function is increasing or decreasing at a point, right? So then we use the first derivative test. Like, okay, once we had our critical values, then we would look at the first derivative on either side of a critical value, all right? And then if the derivative went from like positive to negative, if the derivative goes from like positive to negative, that means the function goes from increasing to decreasing. Um, that means we have a local max. And if the derivative goes from decreasing to increasing on either side of a critical value, that means we have a local min, right? So that was using the first derivative. So let's look at the application of the second derivative. Okay. So using the second derivative to find max and min values, suppose that a function whose derivative f prime exists at every point on an open interval I, then we say that f is concave up if f prime is decreasing, right? So in other words, if the second derivative is positive, it's like the cup opens upward. Like you see how it kind of it's like a cup and the cup is opening upward. So we would say that that's concave up. When the second derivative is positive on an open interval, we say that the function is concave up. When the second derivative is negative, then we say that the function is concave down, right? So the cup opens downward. Okay. So if the second derivative is positive, the function is going to be concave up. So the cup opens upward. If the second derivative is negative, then it's concave down. It opens downward. Okay. So suppose that a function is differential for every x on the open interval, and there's a critical value c, such that f prime of c equals 0. Then f of c is going to be a local minimum if the second derivative is positive, right? Let's see. If the second derivative is positive, that means it's concave up. If the cup opens upward, that means we have a local minimum, right? If the second derivative of that critical value is negative, that means it's concave down, which means the cup opens downward, which means we have the peak of a mountain, so that's a relative max. If f for f where the second derivative is 0, the test can be used to determine where f of c is a relative extrema. Okay. Okay, let's just kind of keep going. So we're asked to graph this function and find the relative extrema. Well, off the bat, we have like the y-intercept should be negative 13. It's a cubic function, and the leading coefficient is positive, so that means it should go up to the right, and because it's the highest exponent is odd, it should go down to the left. So we're expecting, we're kind of anticipating maybe an S-shaped curve. Y-intercept is negative 13. It should go up to the right, down to the left, and then we could try to find the x-intercepts. We could factor out, we get x plus 3, but we don't have anything common there, so I'm not going to try to find the x-intercepts here. But then we can look at the extrema to find like relative max and min, and then talk about its concavity, right? So let's at least look at the derivatives. Give me a second. So if we take the derivative, that's going to give us 3x squared plus 6x minus 9. Okay, let's find our extrema, right? So if we set this to 0, so again, this is a polynomial function, so it's not going to be undefined, but we can set it to 0 and solve. So if we say 3x squared plus 6x minus 9 equal to 0, we can divide both sides by 3. We'll get x squared plus 2x minus 3 equals 0. So then we want to see, okay, can we factor it into something of this nature? One's plus, one's minus, 3 and 1, right? Positive 3 and a negative 1. So then our critical values could be what? Negative 3 and 1, right? So then to do the first derivative test, let's do it like this. So let's plot these critical values. Here's our negative 3. Here's our 1. So let's look at, let's say like let's consider, first let's look at f prime. So here, this is going to be a 0. These are both zeros. So to the left of negative 3, we could do something like negative 4, right? So then when x is negative 4, notice this is going to be negative, this will be negative, double negative is positive, right? So when x is negative 4, f prime is positive to the left of this. So that means our function should be increasing to the left of negative 3. Let's see, between negative 3 and 1, we can do 0. So if we plug in 0, the final result is going to be negative 3, which is negative, right? So the first derivative should be negative between here. So that means our original function should be decreasing. Okay? And then to the right of 1, let's choose something like 2. If we plug 2 in, this will be positive, this will be positive. So the first derivative is going to be positive to the right. So our function should be increasing. Okay? So the first derivative test tells us that when x is negative 3, that should be a relative max. When x is 1, that should be a relative min. Okay, and so I just want to go ahead and look at the second derivative, right? Let's go ahead and look at the second derivative. So let's just take the derivative of the first derivative. I'm kind of running out of space. I'll go this color. So then f double prime is going to be okay. That's going to be what? 6x plus 6, right? So then if we look at the second derivative, this tells us which way the curve, does the curve open up or does it open down, right? So for instance, if we plug negative 3 in here, 6 times 3 is what, negative 18? The result's going to be negative. So here it is. So the second derivative here is going to be negative. That means we have concave down, right? If we plug 1 into the second derivative, we get a positive result. So it's going to be concave up, which makes sense, right? If this is a local max, then that it should be concave down. If this is a local min, it should be concave up, right? So then another thing that we can get from the second derivative, so there should be some point between these critical values where it goes from concave down to concave up. That's called the point of inflection. That's going to occur where the second derivative is either 0 or undefined, right? So if we solve for when the second derivative is 0, I think it's negative 1. When x is negative 1, that should be a point. It's called a point of inflection. So when x is negative 1, let me see, f double prime is 0, when x equals -1, right? So we have a lot of information here. I'm gonna choose another color, just trying to get it all to kind of be separate before I go to another page. Let's see, so the y-intercept is gonna be -13. We have what, a max value? When x is -3, the corresponding y is, so we gotta find that value. Let's see. So it looks like the first one is what, -27, 9 times 3. So those two cancel, right? -27, no. Yeah, plus 27. So those are gone. 9 times 3, so that's 27 minus 13. And 7 to 7 is 14, right? 14. So when x is -3, it looks like the y is 14. So that should be a relative max value. A relative minimum value, when x is 1, that's going to be 4. 4 minus 9 is -5. That's going to be -18. Okay. Oh, and then we have a point of inflection. Point of inflection. We said that occurs when x is -1. So when x is -1, the corresponding y is, let me see, that's -1. So 3 minus 1 is 2. Plus 9 is 11. Minus 13 is -2. Okay. So these are some simple points that we were able to get with minimal effort. X-intercepts here look like they might be a little bit of a challenge. What I would do is plot all of these points with their corresponding features, and then choose a few additional points between and beyond all of these values, right? So let's see if we can put all this together. Let me get a copy of this. Actually, let me get a copy of nope, that's that one. I need both of these. Well, let me just start with this. Copy. This is page 7. Okay. And also, I need a copy of that. So let's do it like this. I really just need the function. I was about to get a whole bunch of extra stuff I didn't need. Okay, so then let me do like this. I want to do some paper, graph paper. Actually, x. So we got these values. Let me choose a few additional points, and we'll put it all together. So I'm going to make a table, right? I'm going to do my table horizontally. So I'm going to have like some x and a y. Let me see. X is right now we have -3. So we'll do like when x is -4, -3. We'll do -2, -1. We'll do when x is 0, 1, and 2. So what I did, I tried to choose, make sure I captured all of the x values that you see in purple, and I also wanted to capture a few x values between and beyond those x values, right? And then I want to find the corresponding y. So to find the corresponding y, I'm going to use, I'm just going to use my calculator. All right. Okay. So let me pull up my Trusted Dusty Rusty and share it with everyone. Come on. Yep. I need to update the grade book because you guys are taking an exam right now. Reload and refresh. Okay. So what I'm going to do, in my upper left hand corner, I'm going to go to my y equals, and I'm going to type the original, which is this x to the power of 3, plus 3x squared minus 9x minus 13. Okay. And then I'm actually going to go to my table. I'm going to go to table. Okay. We should be able to confirm a lot of our numbers. So we started when x was -4, right? So this said, the table says when x is -4, we get a result of 7. We get a result of 7. Let me see, -3 should be 14. Okay, we got the same thing. -2 is a new one, so that's 9. Okay, and that is behaving like a local max, okay? -1, we got -2. They got it, okay, so -2. When x is 0, we got 13, -13, okay? When x is 1, we got -18, and so do they. And when x is 2, they get -11, okay. So then let's plot all these. So notice our x's, we have them go from like -4 to 2. The y's go from like we can go from -20 to 20. So let's do this. I'm gonna get rid of the calculator for right now. Okay. I'm gonna put my origin about like here, all right? So on the y-axis, I wanna go up and down to 20. So I wanna go like 2, 4, 6, 8, 10. So that's 10. Maybe I have to count this a little bit different. Let's count it like this instead. Let's go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, right? So then let's get a copy. Nope. And then on the x-axis, we don't have to go as far. -5 and like we go 5 on both sides. So I'm gonna just write those. So we can go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the positive x is in this direction. I really like the updates they've done with this. I'm gonna copy. I'm just gonna paste. And I'm gonna just do it like this. So this goes like there. And this goes like there. And let's move it a little bit closer. And that goes there. Okay. So this is the positive x. This is the positive y. I think this is our origin. This was 1, 2, 3, 4, 5. So this was -1, -2, -3, 4, and 5. Then I think we went 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay. So let's plot all of these. We can just plot all of this, right? I'll do it in blue. So we had, let's do our y-intercept. Let's see, we had this y-intercept was -13. So that's going to be here. Actually, let me change up my paper. Okay. When x was -3, we're at 14. 2, 4, 6, 8, 10, 12, 14. So that's a max value. So we got, this was a -3, 14. This was the y-intercept of 0, -13. We had a minimum value, a relative min was 1, -18. So here. Okay. We have a point of inflection at -1, -2, which is like here. Okay. So that's where it should go from concave down to concave up. And let's plot these other points. So we had -4, 7, 2, 4, 6, So then 7 would be here. Okay. I think we did negative 3, 14 already. Negative 2, 9. 2, 4, 6, 8. So 9 is there. Negative 2, 9. Okay. Negative 1, negative 2 is plotted. 0, negative 13 is plotted. 1, negative 18 is plotted. And then 2, negative 11. So again, like to find the x-intercepts from college algebra, we can do things like Descartes rule of signs to determine the possible number of positive and negative zeros. We could do the rational zero test to say, hey, if it has any rational zeros, it's going to be somewhere in that list. We can do the upper and lower bound test. There's a lot to find zeros of polynomials, right? So that's why I'm trying to just keep it as simple as possible. And then so if we connect these with a smooth curve, we'll get something like this. And this is still a rough sketch. To make it look a lot more accurate, we could actually find those x-intercepts. But for right now, I'm just going to do this. Okay. So let's notice all of our features were highlighted. The y-intercept was negative 13. You see it there. Max value, negative 3, 14. You see it there. Relative min, you see it here. Point of inflection, where it goes from concave down to concave up, is here. So on and so on, okay? So that's us doing it by hand. Let's compare that to the computer-generated notes. Okay. So first we found f prime and f double prime, okay? So here, I think we got that same thing, and we got this one as well. Come on, why are you still showing? Okay. So then we set f prime to 0 and solved, and we got negative 3 and 1, so these are the critical values. Second derivative, so they did the second derivative with those critical values. Notice that when x was negative 3, the second derivative was negative, so that means we had a relative max, right? So we actually did both tests. We did the first derivative and second derivative test. You don't necessarily have to do that. But sometimes, one might not work. So it's good to have both of them ready to go. Here, the second derivative was positive, so that means we had a relative min. So then, we found the corresponding y's for each of those critical values. So relative max, relative min. See that point of inflection there where the second derivative is 0, and then a few additional points, and they get a graph like this. Okay. So that was fun. We did it by hand and got a computer generated one. Notice that they do have the y-intercept. They did not find the x-intercept just because it was being too much. So, you just try it. I mean, and we could investigate further, but we're just exploring some concepts, ideas, and notions. Oh man, energy level. I gotta stop eating that junk. That's why I feel like junk. Okay. So this one we're asked to graph this function given by this and find the relative extrema. Oh, we already have the derivative. Darn it. And I didn't cancel it. Okay, that's okay. Well, let's confirm those. Let me make a copy of this and just blot that out. I mean, even though we can see it, but I still want to practice. Let me just, they have some new features. Let me just copy the whole thing, and I want to paste it right here. So then here, what I'm going to do, I guess it'll be okay for now. Okay. So let's start by, even though I know we already saw the answers, but let's find those, right? Let's find k prime and k double prime. So k prime of x, right? So the derivative of e is going to be itself. So that's going to still be e to the 2x times the derivative of the exponent, so times 2. So that's going to be 2e to the 2x minus e to the x, all right? That's the first derivative. Yep. And then the second derivative, k double prime, again itself, 2e to the 2x, again times another 2, so you know that's going to become a 4. Okay, and then still minus e to the x, because the derivative of e to the x is itself. Okay, so then if we set k prime equal to 0, we're going to have 2e to the 2x minus e to the x. If we set that equal to 0, let me see. So e to the 2x, I'm not getting a 0. Let me think about it. What am I doing wrong? Because if we have e to the 2x, right? Say we had e to the x. Say we had this. I'm just thinking out loud. If we had e to the x squared, right? A power to a power, and you multiply, right? So, I was trying to see if we could factor out a e to the x. And I think we can. So what I'm thinking, it looks like this is going to be e to the x times 2 e to the x minus 1. All right? That's what I'm thinking. I'm going to, just for the sake of space, I'm going to clear this out. I'm going to go with it, and we'll fix it if it's not right. But then e to the x is never 0 because there's a horizontal asymptote on the x-axis, so the first thing can't be 0. Let's see what happens if we set the second thing to 0. You get e to the x equals 1/2. Take the natural log on both sides, x equals negative natural log of 2. Okay. So I think that's the only critical value that we get, right? Whatever that number is. Okay. So then if we evaluated the second derivative here, if we plug whatever that number is into our second derivative, then we see, okay, is it positive or negative? Let's see if we can get an exact result. So then if we look at k double prime of this negative natural log of 2, this is going to be 4 times e to the power of 2 times negative natural log of 2. Now, you know, minus e to the power of negative natural log of 2. Okay. Let me see. Negative 2, so 2 to the power of negative 2. So that's 1 over 4, right? Let me kind of rewrite this. Hopefully this is okay. So this is the same as 4e to the natural log of 1/4 minus e to the natural log of 1/2. So the e and the natural log are inverses of each other. They cancel each other out. That's like 1. So it looks like it's going to be 1 minus 1/2, which is 1/2, which is positive. Okay. So if it's concave up, that means we should have a relative min. Should be a relative minimum value, right? So it looks like, okay, I think I'm gonna use the notes, right? But x equals the negative natural log of 2 is our critical value, and then the second derivative of that was positive, so that should be a local minimum, right? Okay, so then we would make a table and just plot a few additional points around those critical values. Okay, so I think we got those results, so I'm gonna let that be. Now, so again, with the type notes, they set the first derivative to 0. They did the same thing. They got this, right? E to the x times, we got the exact same thing. This is always positive. So we only got a result for the second one. E to the x equals 1/2, so natural log of 1/2. I think we wrote it as negative natural log of 2. They're the same thing. But it's the same, it's going to be the same number, right? Second derivative test. So k double prime of that number and they get a half like we got, which is positive. So that means we have a relative minimum. I think that's what we said, right? So then we find the ordered pair. So you get natural log of a half, you get a negative 0.25. That's the ordered pair. That's going to be a relative min. And then again, I would just make a table to choose additional points, and you should get something like this. Okay. Let me see my time. Okay, I think we're okay. Okay, so that one, was a little bit of fun. I'm going to leave this as an exercise just so we're not using so much of our time. Okay. So points of inflection, I know we already did one. I kind of introduced it already, but I guess it's a formal introduction. If a function has a point of inflection, it must occur at the point x naught where the second derivative is 0 or the second derivative does not exist, right? So the point of inflection is where a graph goes from concave up to concave down. And that's going to occur when the second derivative is either 0 or it does not exist. Okay. Okay, so let's kind of go through this strategy for sketching graphs, right? Because it gives us a methodical way to kind of approach these. So first we determine the derivatives in domain, find f prime and f double prime, and then note the domain of the original function. Then we can look at the critical values. The critical values are found by solving f prime equal to 0 and finding where f prime does not exist. And then find the corresponding y's for these critical values. To determine whether the function is increasing and or decreasing, or to identify a relative extrema, so you can set the critical values from step B into the second derivative. If you get a positive result, that means it's concave up. That means we should have a relative min, and then or reverse everything. So then we have inflection points. Inflection points are going to occur where the second derivative, where the graph goes from concave up to concave down, or vice versa. So that's where the second derivative is going to be 0 or where it does not exist. Find the corresponding y values for these points of inflection. And then use the candidates for inflection points from step B to define intervals, and then use the relative extrema from step B to determine where the graph is concave up and where it's concave down. Okay. And then sketch the graph, right? Let's try, hopefully we can get like a couple of these in. Find the relative extrema given by this and sketch the graph. Okay. So first thing again that I would do is look at your derivatives, all right? So let me just make a note, derivatives. Okay. So if we look at f prime, that's going to be 3x squared minus 3. If we look at f double prime, it's going to be 6x. I think the second thing was critical values. Okay, so let's look at critical values. Can we find any critical values? Okay. So like if we set the first derivative to 0 and solve, we're going to say 3x squared minus 3. We want to set that to 0 and solve. X squared equals 1. So then x equals plus or minus 1. Okay. So some candidates to be critical values, let me see, will be the order pair. So when x is negative 1, that's going to be negative 1 plus 3 is going to be 2 plus 2 is 4. When x is 1, 1 minus 3 is negative 2, that's going to be 0. Okay, we found the x-intercept. We might be able to use that to find others, but that's okay. So these are candidates for critical values. So then we need to determine if it's an extrema with the second derivative test. Let me see. Yeah, so second derivative test, I'm going to say, I'm just going to say extrema. Okay, so we're going to take those x values and plug them into the second derivative. So when x is -1, we get a negative result, which means it's concave down. So we have a potential max at x equals -1, all right? When x is 1, if we plug 1 into the second derivative, we get a positive result. That means it's concave up. That means we should have a relative minimum value at x equals 1, right? So the first one should be a max, the second one should be a min. Okay. So let's look at points of inflection. So point of inflection, it should be the fourth one, right? Yeah. That's where the second derivative is 0 or undefined. So then 6x equal to 0, so x will be 0. So point of inflection should occur when x is 0. And I think that's going to give us the y-intercept is going to be 2. Okay. All we did, we set the second derivative to 0 and solve. We got x equals 0. Then the corresponding y when x is 0 is 2, right? And then we could look at concavity. I think we've already looked at it though. So to the left of 0, I think it was concave down, and to the right of 0, it was concave up. I'm using basically part 3. So then the graph, right? Let me do this. I'm going to add a page and change the view. So let's see our x values. I feel like it was a little bit neater when we put it in table form. Right now we only have the 3 points though. Plus or minus 1, 0. I kind of want to do a few additional points. I'm going to make a table. So I'm going to go my x versus my y. Right now we just have 3 points. So I'm going to start at I start at -3. -2, -1. Actually, I want some points between the -1 and 0. So what I'm going to do, instead of starting at -3, I'm going to start at -2, then I'm going to go -1.5, -1, -0.5, then I want to go 0, and then I want to go 0.5, 1, 1.5, and then 2. I want to do those values so we can get, because I want points between and beyond the original points that we found. Okay. I'm just going to use the calculator. That just seems more simple. Okay. So I went to my y equals. The original, we got this x to the power of 3 minus 3x plus 2. Okay. I want to set the thing for my table. I want the table to start at let's start at -2, and we want it to change by 0.5. Okay. And I want to graph, not graph. I meant to go to table. Okay. So yeah, we get some funky numbers, but that's okay. When x was -2, we got 0. Then here we got 3.125, 4, -0.5 is 3.375, 0 was 2, that's correct, 0.5, 625, 1, we got 0, 1.5 we get 0.875, and then 4. Okay. So then if we were going to plot these, x is -2 to 2, y's, it looks like the max So it was like 4. And the minimum was 0, so none of them are negative. Okay. So we can go, I'm gonna let this be my origin about here. We need to get up to like 4, so I'm gonna go to like 5. I'm gonna go 1, 2, 3, 4, 5, and 6. We don't really need to go down that much because we don't have any negative y values. And then we need to get over to plus or minus 2. Let's go, that's a half, that's 1, that's a half, that's 2, and that's 3. That's a half and that's 1, a half and 2, a half and 3, okay? Positive x is in this direction. Positive y is in this direction. Okay, and let's label this. So we did the origin. I think we went 1, 2, 3, -1, -2, -3. 2, 4, 6. No, 1, 2, 3, 4, 5, 6. We went 1, 2, 3, 4, 5, 6. 1, 2, right? Okay. So then if we plot these points, -2, 0, so we have something here. -1.5, 3, and 3, right? Let's see, that's 3. This is 3.5, so somewhere about like here. This was -2, 0. This was -1.5, 3.125. Okay. -1, 4. Here. Okay. A half and 3.375. It's about here. Okay, it's a little bit jammed, but you should be able to tell what that is. 0, 2 is here. A half, 0.6, so a little above half is about here. Okay. 1, 0 is here. Was that when x was 1, so that was a minimum value? Okay. And then 1.5, 0.875 is about here. Okay. And then over 2 and up 4. 2. Okay. So then if we connect it with a smooth curve, we'll have something like this. There's a point of inflection. Okay. So to kind of recap, we found the critical values of plus or minus 1. We found the corresponding y's. Then we used the second derivative test to tell if those were relative max or min, okay? Because if it's a max, then it's going to be concave down at that point. If it's a min, it's going to be concave up at that point. We also found our point of inflection by setting the second derivative to 0 and solving. We found a few additional points between and beyond all those original points, and then put all those together to get a graph. Okay. Let's go view. Go back to this one. Okay. Let me see what our time is looking like. I think we're almost done with this one. Well, we got a good amount of slides. I might try to do one more. Let's see. So the derivatives, I think we got those. Critical values, plus or minus 1. So 4 and 0 with the corresponding y's. First one was negative, so that was a relative max. Second was positive, so that was a relative min. The second derivative were, those. Okay, so that's just kind of recapping. Point of inflection, you said the second derivative was 0 and solve. So when x was 0, y was 2. Okay. So you see a table. It probably chose better points than I did, but because you get the gist. So once we had those points, we just chose a few additional points to kind of plot, and we'll get something like this. And I think we got this exact same graph. Okay. I'm going to leave this quick check as exercise for you. Okay. I just realized I think I need to load the notes from the last class and this one. Graph the function given by this. List the coordinates of any extreme points. State whether the function is increasing, decreasing. Okay. Let me give myself. I'm gonna see what I can do. Let me give myself some space. Okay. So, if we kind of do what we just did, let me go back, change my paper. So first let's look at derivatives, right? So then f prime, let's see, the exponent comes down, the inside stays, we subtract 1, so that's going to be a negative 2/3, times the derivative of the inside function, so that's going to be times 2. Okay, so what I'm going to do is just change this 1 to a 2. And that's it for the first derivative. If we look at the second derivative, exponent comes down, that's going to become negative 4/9. Inside stays, subtract 1 from the exponent, so negative 2 minus 3 is negative 5. Times the derivative of the inside is going to be times 2, so that turns the 4 into an 8. Okay. So then, critical values, I think that was the second one. I know that's what I feel inclined to investigate. I'm going to say critical values. I don't know what I'm writing. Critical values. Okay. So basically set the first derivative to 0 and solve. So we're going to have this 2 by 3 times this 2x minus 5 to the negative 2/3. We want to set that equal to 0. So let me, because it has a negative exponent, it actually goes to the denominator. So we have, this is the same as 3 times the cube root of 2x minus 5 squared under 2, right? So that won't be equal to 0, but it might have a point where it's undefined, right? Because in order for a fraction to be 0, the numerator would have to be 0, right? And this numerator will never be 0. So, but what we can look at, we can see, okay, well, what x values will make it undefined, namely, what x values will make the denominator 0. So the denominator is only going to be 0 when that radicand is 0, all right? So if we set 2x minus 5 equal to 0 and solve, add the 5, x equals what? 5 by 2. So when x is 5 by 2, it'll make a 0 in the denominator and it'll be undefined, so that's our critical value. I think that's the only one. Okay. So then we should find the corresponding y. I'm just going to kind of let that be for right now. So then we want to see if it's an extrema or not. So the third thing I'm going to say is extrema. Okay, and basically plugging that into the second derivative and seeing if it's positive or negative, right? So we want to look at f double prime of this 5 by 2 and see what happens. So there's going to be a negative 8 by 9, 2 times this 5 by 2 minus 5 to this negative 5/3. Kind of ran out of space there. That's going to be equal to 0. So at this point I got negative 8 by 9 times 0 to the power of a negative 5/3, but I think that's going to be undefined, right? Because it's going to be 1 over 0. So I'm going to say undefined, or does not exist. Okay, exist. Okay, so I think that maybe we cannot use the second derivative test. Let's look on either side of this 5 by 2 and look at the first derivative, right? So for instance, 5 by 2 is what? 2.25? So something to the left of 5 by 2, let's do when x is 1, right? So I'm going to do this in this color. Let's look at f prime of 1. So if we plug 1 into the first derivative, we'll get 2/3, 2 minus 5 to the negative 2/3. That's going to be a negative value. We're doing cube root. So when we square it, it becomes positive. It's going to be positive. Long story short, this number is going to be positive, right? You can use your calculator. You should get a positive result. Okay, so on the left, the function is increasing. Let's choose a number to the right of this critical value. So if this is 2.5, we can choose something like 3. So let's look at f prime of 3 and see what happens. So that's going to be 2/3. That's going to be 6 minus 5, which is 1. So it's going to be positive, right? And so we're not getting that sign change. So it seems like this doesn't have any extrema. That was a candidate. Let me see. I think that's a point of inflection, but we're not getting it to go from, let me see. I guess we'd have to look at the second derivative there. That one, I would just look at the graph, or like graph it. Let's, but we're not getting that it's an extrema. It's like we're getting that it's neither a relative max nor a relative min. It could be a point of inflection. But I'm not going to check it now because I'm kind of exhausted. Let me go paper. Let's see what's going on. So the first derivative, I think we got this, right? The second derivative, I think we got this as well. Negative 8 by 9, 2x minus 5 to the negative 5/3. Okay. The domain is all reals. So since this is never 0, the only critical value is where this doesn't exist. This is what we got. So that's where the denominator is going to be 0. And so they get the 5/2. We got that. So then when x is 5/2, the corresponding y value is 1. We could find that, I just didn't do it. So then we want to see, like, is it increasing, decreasing, or do we have any extrema? We can't divide by 0. We got the same thing. So since it doesn't exist, the second derivative test fails. Instead, we use the first derivative test. Okay. So we got the same thing. We got this does not exist or dividing by 0. So then we went back to the first derivative and looked on either side of this critical value. So to the left, they chose 2, which is positive. On the right, they chose 3, which is also positive. So it's not an extrema, which is what we got. All right. And that's why I stopped. I think we could still graph it by choosing like several x values and plot the points, but it's not an extrema. Okay, since f double prime is never, we only need to find out where it does not exist. And since f double prime cannot exist everywhere, f prime does not exist. So this is a possible point of inflection, right? So I guess we should have kept going to we would choose something to the left, plug it into the second derivative. They got a positive, and then they got a negative. So it is an inflection point. We mentioned it. We didn't investigate. We could have, but and then you get something like this. It goes from concave up. See how the cup opens upward, to concave down, right? But it's not a max or min. It's always increasing, right? The graph is always going up. Okay, that was an adventure. Okay, and then you see they also, so once they did the second derivative test to determine if it's a point of inflection, they still went on and made a table, chose several values of x, found the corresponding y, plot the points. That's about all you can do, all right? Because you know it doesn't always work out like super neat and clean and stuff like that. So you have to just like test it, go with your results, check your work. You know, you see how this one, it was neither a relative max or a min. Um, it did turn out to be a point of inflection, and even when we tried to use the first derivative test, it was increasing on both sides. So we did identify, well, we didn't, but you know, it was identified as a point of inflection. We found a few additional points, found the corresponding y's, plotted them, and everything actually does line up based on what we were finding, right? Okay, so hopefully your brain isn't mush like mine is. I was about to say your main isn't bush. Totally like, you know, being dyslexic, momentary dyslexia. But I do kind of have a headache. So, but yeah, that was an adventure. Okay, it is what it is. As a quick section summary, the second derivative determines the concavity of the graph. So that tells you, does the curve open up or does the curve open down? If the second derivative is positive, we say that's concave up. If the second derivative is negative, we say that's concave down. If the critical value, when we plug in that critical value, if it's positive, then it's going to be a minimum. Because if the second derivative is positive, that means it's concave up. That means we're talking about a minimum value. If the second derivative of that critical value is positive, that means our function is concave. Wait a minute, something's not right here. If it's positive, it's concave up. That should be a min, right? I think this is a typo. That's supposed to be switched around. If the second derivative is negative, it's supposed to be concave down, which would be a max. So I think this looks like a typo. Matter of fact, I'm just going to make it rough. Or what I could do, I could take this one, copy, paste the image, and then just like that. Technology boy. Okay, I think that's, if it's negative, it's concave down, then we have relative max, right? All I did was copy the right thing and paste on top of the wrong thing. That's so interesting. Anyway. And then the point of inflection is where the original graph is going to go from concave up to concave down or vice versa. And that's going to occur when the second derivative is either 0 or undefined, right? So we still want to test for our point of inflection. We got a little bit lazy on that last one, but you saw where they still tested it for the point of inflection, and it did turn out to be a point of inflection. And so then we just found a few additional points, plotted the points, and confirmed our results. Okay? That was an adventure. All right. So on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.